And next up we have David Buscher, who's going to tell us all about the Magdalena Ridge Interferometer.
Right, thank you very much. I'm here to tell you about the Magdalena Ridge Observatory Interferometer, which is a system that's being constructed in New Mexico by a collaboration between New Mexico Tech and the University of Cambridge. So it's actually quite a small collaboration that's building quite a big interferometer. So I'm presenting on behalf of the MROI team. There's 5 of us in the room here, and I'll point out some of the things that they've done. But I'm going to give you mostly a Cambridge-centric point of view, not necessarily going to tell you about everything that everybody's doing on the project, but just to say, give the UK audience a UK flavour of these things. So what is the MROI? Well, first of all, the Magdalena Ridge Observatory is a observatory. Unfortunately, can't quite see it as well in this. It's on top of a mountaintop, which is at 10,000 feet in New Mexico. Actually, if you pan this photograph a little bit to the right, you'd see down about 3,000 feet below you, you'd see the very large array, the radio interferometer. But this is an optical interferometer built on top of this mountain. It turns out, yes, it is an observatory in the sense that there's more than one telescope. You can see right at the back. So where's the pointer? Oh, there it is. Sorry. Yes, right at the back here is actually a 2.4 meter telescope. So it's just an ordinary single telescope, although it actually slews at, I can't remember now, it's 10 degrees a second or something like that. So it's really quite a fast telescope. But yes, the interferometer is the biggest part of the observatory. And this building here you can see is a 200 meter long delay line building. And then inside here is the beam combination optics for the interferometer, or at least the location, the lab for the beam combining optics. So let me just tell you about, briefly about what the interferometer is actually designed to do. It's basically a visible to near-infrared interferometer. Hearing Sasha's talk today made me think, yes, we really do want to go to the L band as well, but currently it's designed to go out to the K band. It has roughly the same baselines as Chara, so you get about 0.6 milliarcsecond resolution. The things that make it stand out from any other interferometer is, first of all, the limiting magnitude. People are asking about how bright is bright these days, and bright now is, we're saying, is 14th magnitude, not 10th magnitude, is where we want to get. And the other big thing is, if you want to make an image with the VLTI, for instance, then you can take a single configuration of VLTI, run it for a night, and you get most of the data to get sort of moderate image. But if you want to get a real image, so with lots of pixels in it, you actually have to move the telescopes about, wait a few weeks until you get to the next configuration, take some data in that configuration, and so after a few weeks you'll have one image. The aim of MRI is to be a proper imaging interferometer, so the idea is to make, roughly speaking, 50 images a night. And so that's a huge leap in the way people do interferometry. So just to talk a little bit more about, yes, what is this imaging mission? What do we do? And it's very simple. To do imaging fast, you need lots of telescopes. That's all there is to it. And so the MRI is the only interferometer which is actually designed to run 10 telescopes simultaneously. That's the point, is that you can run them simultaneously. You can put 28 telescopes on the site, but you can run 10 of them simultaneously, which means if you take your 10 telescopes and ask what's the instantaneous UV coverage you have, it looks like this. So you've got a pretty filled-in UV plane in a single snapshot. So that's why we can do so many images a night. You don't have to wait for the Earth to rotate. You just get all the UV coverage essentially in one go. Then you add to that sensitivity, then you make, I think, a killer combination. So the beautiful results we've been getting from gravity on AGNs, for instance, has been looking at, so this is a plot of the number of targets you get versus the magnitude of the reference source. Now we're talking about, because with things like gravity, you can use a reference source which is bright and then observe a fainter object if it happens to be nearby. But we're talking about what is the brightest reference object in the field. And so these are looking at objects around 12. But you can see if you extend up to 14th magnitude, you can access many, many more objects. But what's more important is that we can now access many, many more objects and do imaging on them. And that's really, really a very powerful thing to do on long baselines, which you can't do with the VLTI. The VLTI, if you're going to go faint, then you're restricted to to the 100-meter baselines. We can go to the 350-meter baselines and have lots of telescopes simultaneously on that. So this I think, where it's the combination of being able to go faint and then do the imaging that's the real killer feature. And part of the reason, I mean, there are many ways that we actually get the sensitivity, but part of it is to do with just the simplified optical train. Because MROI was designed with a single aim in mind, i.e. getting as faint as possible, we've eliminated everything that might add fancy features, but also take away the number of photons. So basically, if you ask how many photons, how many reflections there are in this optical train to get to the science combiner, you can compare with in Chara and I think VLTI is pretty similar. You have about 40 reflections. In MROI, there's 13. So that's where we're getting a lot of the sensitivity from, and it's that combination of the sensitivity and the imaging that makes it a very useful scientific instrument. And it turns out that actually the combination of an imaging capability and being able to go faint allows you to ask for money from other people who might be interested in looking at non-astronomical objects, things like this. So it turns out that looking at a geostationary satellite, once it's been deployed, to figure out if it's deployed okay, actually you can't do with any sort of current system. Basically because these objects are actually both faint and very small, at least compared to what you can do with a conventional telescope. They're actually quite large for an interferometer. That's actually one of the problems in using any current interferometer to observe one of these geostationary targets. They're actually a few hundred milliarcseconds across, which is like huge. So it turns out that MROI actually occupies a bit of phase space which no other interferometer can get to, which happens to correspond to all the objects in the geostationary orbit. So I look back at my records and realize that this is the first time I've talked about MROI to a UK audience since the last special discussion meeting on this topic. So I'm just going to update you all on where we are since then, what's happened. So at the last specialist discussion meeting, we were actually talking about shipping the first delay line to MRO, and in fact, we did ship it, and we tested it out, and in 100 meters, so the delay lines are designed to run inside 200 meters of vacuum pipe. The first 100 meters have been constructed, and this was tested out in the first 100 meters of pipe, and it works very well. We had a few issues with the wireless communication inside the pipe, and we've just recently had a sort of a rescue mission, as it were, to sort those out. So now it runs perfectly well over the entire 100 meters. This is just a nice picture of the 100 meters pipe. This is one of the people at New Mexico is a photographer who likes lighting up things. So this is 100 meters of pipe going down. This is going down this 200-meter building. At the end of the building, you can just about see over there. But yes, the trolley runs inside this vacuum pipe, which serves both as the vacuum enclosure, but also actually as the precision rails on which the trolley runs. The other really big thing that's happened is we've now got the telescope, the first unit telescope. It's a 1.4 meter. It's an unusual design. It's an alt-alt design, which is designed specifically for interferometry, because you can basically get the light out of the telescope into a fixed direction in 3 reflections, which you can't do with a conventional alt-az. It's also a very nice telescope all around. It has a very high wavefront quality and all those things. So this is it being tested out in actually the maintenance enclosure, and this is the true enclosure for it that arrived on the mountain in June, I think, of last year. These enclosures are also quite specialized. They have this funny slit, but that's for many reasons. So you can one of the things is because you can close pack the telescopes next to each other. They don't shadow each other. But the other thing is actually you can lift up the whole enclosure with the telescope inside it, and you can move it to a new location, so you can increase your UV coverage, or actually change your UV coverage, more importantly, for looking at different scales of objects. And then the two things were actually united on the array. Well, actually, they were united and then put onto the array, transported as a whole onto the array. So this is the enclosure sitting on the array with the telescope inside it. So this is the first few pads of the innermost pads of the array have been populated, and they're beginning to build out the vacuum lines which bring the light from the telescope into the array. And this is the telescope sitting inside its enclosure. As you can see, it's quite cramped inside the enclosure. It's quite hard to get a picture of it, but that's how it is. And then, yes, to actually test out the telescope in anger, you need something that is good for high-resolution imaging, and with only one telescope, the closest thing you can do is adaptive optics, which is a tip-tilt system in this case. So this is the tip-tilt system on the Naismith bench of the telescope. You might recognize that person there. And then with the tip-tilt system, actually had its first light on the telescope. And this, at this point, was actually a huge major point of risk reduction in the whole interferometer. Basically, the first time we actually looked at how good the image quality essentially is inside an enclosure with our actual telescopes. And what was very nice is, yes, you all know the thing of you make some seeing measurements on a site, you think, gosh, this is a really good site, you put a telescope on it, and you realize the seeing you get inside your telescope dome is nowhere near what you got in your measurements. We were pleasantly surprised to see, well, first of all, is we opened up the dome and had a dim running at the same time. And you can see here, we're actually getting at some points down to 0.4 arcsecond seeing. The dim measurements are obviously external to the dome, but these measurements here are by the fast tip tilt system. The blue measurements are the fast tip tilt system, and it's showing that in fact, there doesn't seem to be significant amounts, at least, of dome seeing. There we're actually seeing sub-arcsecond inside the dome on the first time we open the dome, which is really quite nice. And yes, you see there are actually 3 nights of data. They all show sub-arcsecond seeing, so that's a really good start. And another really good start is the first time that we ran the tip-tilt system on the sky. We achieved our requirement, which is roughly equivalent to about a little bit over 50% strail for 12th magnitude objects. So again, the system is working pretty well. I mean, it's actually not working to its design specifications. So there's a couple of magnitudes more to go, but I think if we work on it, we can get there. So that's basically where we currently are in terms of what's actually running on the telescope. And I'll tell you about things that we're currently building to take it further. One thing that's being built in Cambridge is the automated alignment system. That's basically active optics for an interferometer. Basically, there's at least 10 reflections that need to be actively need to be aligned in order to get light into the system. And so we have a system which actually can monitor at very regular intervals the alignment of all the mirrors in the beam train. And first of all, at the beginning of the night, you can actually align the entire interferometer. So if you have 10 telescopes, you have of order 100 mirrors to align. You can do that all in an automatic fashion rather than having a human try to do that. But then during the night, as things drift thermally, you can realign the system on sort of 10-minute timescales so that the system remains in alignment for the entire night. And that's been worked on by James Lewis, who I think is in the room here, there. Another thing that's being built, this is the fringe tracker called ICON, which allows us to get to these faint limiting magnitudes. This is a diagram of this is a photograph of the inside of the dewar with some beams sketched on it. So that's the dewar has been built. It's being aligned. Most of the optical work has been done in New Mexico, but in Cambridge we're writing the fringe tracking software for that. After the fringe tracker, then comes the science beam combiner. So this is a spectrally dispersed beam combiner. So this shows fringes in this direction and wavelength in this direction. And this is a simulation done by Dan Morton there, who's working on the design of this instrument. It's a 3-beam combiner for the first 3 telescopes. It's just the first science combiner for the system. And we're doing a full polychromatic physical optics simulation of the entire system. And so where does that get us to where we're going to go? So first fringes, so first light we've had on a single telescope, but first fringes is the first time that you actually say you've got an interferometer, obviously. So that's the big goal. We think we can now actually give you a date. I was always very hesitant to give dates for first fringes before because the project is entirely money limited. The money comes from Congress And as you know, getting Congress to agree on anything is particularly difficult, especially at the moment. But we actually have now to the stage where the contract for the second telescope is about to be signed. And so we can reasonably confidently predict the timeline, at least to first fringes. So the first thing that we need to do is so-called PVM3. PVM stands for Performance Verification Milestones. We're just basically trying to, as we bring the system up piece by piece, essentially do the higher and higher integration tests of the system. And PVM3 gets light all the way from the first telescope into the beam combining area and checks that the wavefront quality and the vibration levels and all those things are at the level that we expect them. So that's later this year. And then, assuming the contract is actually signed, which we very much hope it will be in the next week or two, then the second telescope and the enclosure should arrive in somewhere in the middle of 2020, and that we're predicting first fringes in the third quarter of 2020. All things being well, which I think they're looking well so far, touch wood. So once we've got to first fringes, then the timeline becomes again a bit more fluid because we don't actually have the money in our pockets to actually say when the next thing is going to be ordered. But we hope to get a next tranche of money to order the third telescope within a few months. So that hopefully will happen. And so installing the third telescope is clearly the next thing to do so we can actually get a closure phase. But more importantly, actually demonstrate faint object multi-baseline fringe tracking, because one of the things we rely on is the ability to link together multiple telescopes and do fringe tracking, essentially doing Shack-Hartman sensing across multiple telescopes, i.e. using nearest neighbor telescopes to phase up the entire array. And so that we want to demonstrate that. And at that point, that's where the promised funding runs out, i.e. we have 3 telescopes. We can at that point do some early science. We can do non-imaging studies. With 3 telescopes, yes, you can get a closure phase, but you can't really do an image. And at this point, we won't have very long baselines, so we'll only have resolution equivalent to an ELT, no better than that. So we'll be able to do some science, but mainly to do it on faint objects, which is faint interferometrically, of course. Cosmologists wouldn't be very happy with it, but we'll be able to do stuff that hasn't been done before because it's much fainter than any other interferometer can do. But once we get to 7 telescopes, which is that's roughly the breaking point where we basically become an imaging interferometer which is essentially unparalleled anywhere. And we can basically do that 50 images a night type of thing and do it on very faint objects. A very large number of targets are available. And I think interferometry will enter a new age. Right, thank you very much.
So, questions for Dave? Stunned. Can you say how much each telescope costs?
I'm not sure if that's a trade secret, but yes, it's a couple million basically for the telescope itself, but then there's all the bits around it.
Okay. Anybody else? Yeah.
You mentioned a couple of magnitudes of missing sensitivity at the moment. Do you want to go into that a little bit?
We haven't analysed the data well enough to understand where that's coming from. So all I can say is yes, the design sensitivity and the sensitivity in the lab would lead us to think we can easily get 14th magnitude, and so we currently don't know where that missing sensitivity. Some of it's clearly coming from there are losses somewhere in the optics in terms of the number of photons we're getting, which we need to sort out where that's coming from. But there's other losses that we don't understand at the moment.
Okay, if we can thank Dave again.